So, in previous classes we have seen the use of the energy equation, how it can quickly and in a more convenient fashion give us the governing equation for any heat transfer process, be it conduction, convection, a source where heat can be generated, transient effects, and most importantly how to take care of the viscous heat dissipation. So, the dissipation function phi that has also been included in the development of the energy equation, even though we understand that it is going to be irrelevant in most of the cases, unless some very special cases in which there would be a large velocity gradient or we are dealing with high viscosity and so on. Then we have proceeded to obtain the governing equation for forced convection heat transfer in a tube where the sidewall, through the sidewalls, a constant heat is being added to the system. And there we have seen that how easily we could obtain the governing equation through the use of the energy equation. So, we took the energy equation in the radial coordinate system and cancelled out the terms which are not relevant. So, what we obtained is the governing equation, still a PDE, and we could also identify the boundary conditions. Then we have non-dimensionalized the equation, and we took the special case, a special limiting case in which the fluid has traversed a significant distance in the tube, such that we can assume that the profile of the fluid temperature will not change with the radial, will not change anymore. The shape of the profile will remain unchanged. However, a constant amount is going to be added as the fluid front moves more and more into the tube. So, this assumption of that we could separate the R dependence of the temperature profile and Z dependence of the temperature profile as the sum of two distinct functions enabled us to convert the PDE to an ODE. So, we got a limiting solution which is truly valid when eta, the dimensionless variable denoting the actual distance, when eta tends to infinity, but it has been shown that we get reasonably good approximation of the temperature profile even for smaller lower values of epsilon, the actual distance as well. And there we have also seen that two dimensionless numbers, namely Reynolds number and Prandtl number, appear automatically in the governing equation. So, if we have to express, or if you have to represent the data of forced convection for which, let us say it is for a situation for which no standard relations can be obtained. So, it would be customary, it would be expected that the data should be fitted with some function of Reynolds number and Prandtl number. So, the utility, the importance of dimensionless groups has been underscored by the analysis, where we could identify the important terms, important dimensionless numbers in the description of the entire process. Since we have worked with forced convection in the last class, let us try to see what would be the case when we have free convection or natural convection. So, natural convection is there everywhere. Okay, it is the most common form of heat transfer. Even if you do not have any forced flow of fluid over a surface which is hot or cold, you will always have natural convection. So, the process is characterized by a change in buoyancy. So, a change in buoyancy as a function of temperature will create lighter fluid near the top and heavier fluid near the bottom. So, if this is an object whose temperature is different, higher than that of the surrounding fluid, then the fluid closest to the surface, closest to the hot surface, its buoyancy will be changed and therefore it would start to rise, and as it rises its temperature will progressively increase, and therefore and then it would go to the bulk, and whatever is rising from here is going to be replaced by cooler fluid from the side. So therefore a cycle will start in which the cooler air will extract heat from the hot surface, and this process, even though the heat transfer coefficient is significantly lower than that of forced convection, but the ubiquitous nature of free convection would ensure that there would be substantial heat losses even in the absence of an imposed flow, and in many of the conditions you need to take into account the heat transfer both due to forced convection as well as free convection. So a mixed condition most of the times exist when heat transfer is taking place from a hot surface. So the free convection is characterized by no imposed flow, a change in buoyancy resulting in upward, for the case of hot surface, upward flow of the fluid to be replaced by cooler fluid from the surrounding, and thereby it has thereby the heat transfer process continues as long as there is a temperature difference between the hot surface and the fluid surrounding it. So we are going to first start with free convection heat transfer from the simplest possible geometry, that is that of a vertical plate. So let us assume that we have a vertical plate which is in contact with air. So this is the vertical solid plate whose length is h and whose temperature is maintained at a constant temperature of T0. So T0 is the temperature of the solid, and we have the coordinate system as this is the z direction and this is the y direction, and we will assume that in the x direction it's wide enough such that the process is not going to be governed, is not going to be dependent on whatever happens in the z direction. So then what you would have is the air over here has a temperature which is different from the temperature of the solid, and let's assume that the temperature here is at T1. So if you draw the temperature profile for such a case, it would probably look something like this, where it would asymptotically reach T1. So I am plotting T, the temperature of the air near the wall, minus T1. So T minus T1 would slowly approach 0 as we move away from the plate. So this is the temperature profile, or rather the temperature difference profile, which one would expect for the case of a hot plate in contact with a cooler fluid. So what happens is the fluid near the wall, its buoyant force would force it to move in the upward direction, and cooler fluid from the surrounding is going to come and replace it. So there's going to be a motion in this direction and a filling up of the void left by the upward moving fluid by that from the surrounding. So if I draw the velocity profile, it would probably be this is at the, because of no slip condition, it would start with a velocity equal to 0, and then it would rise and then slowly decrease till it comes to be equal to 0. So this is going to be the velocity profile. However, in the drawing it is greatly exaggerated, and this profile would be skewed towards the solid plate. That means ideally it would probably look like something like this. Okay, because of clarity, in order to bring in clarity, I have drawn it in this way, but the peak is going to be towards the solid plate, and that's what the profile would be. So this Vz, the velocity in the z direction, is definitely going to be a function of y. Now the problem statement therefore is that a flat plate heated to a temperature T0 is suspended in a large motionless body of fluid which is at a temperature T1, and we need to find out the heat loss. What would be the heat loss from such a system? in terms of the velocity, in terms of the physical properties, for example mu and k and so on. So, in this case the convection, free convection, this is a case of free convection, and the equation of motion, I am going to write the equation of continuity, which is del Vy by del y plus del Vz by del z is going to be equal to 0. There would be some Vy, otherwise if there is no Vy, then there would not be any replenishment of the hot air that has left this space. So, Vy even small, it would still be present in the governing equation. So, this is equation of continuity, and then I am writing the equation of motion, which is rho Vy del Vz del y. This is the z component, because most of the motion is in the z direction. So, I am writing the z component of equation of motion plus Vz del Vz del z is equal to mu times. So, these are the viscous transport terms. So, this is the additional term which appears in the equation of motion, z component of equation of motion. So, this refers to, this essentially tells us the buoyant force, the expression for the buoyant force, and the beta is the coefficient of thermal expansion. So, if beta is the coefficient of thermal expansion, so beta is simply defined as the change in volume with a change in temperature non-dimensionalized by the volume. So, this is the change in volume with respect to the original volume as a result of change in temperature. So, I can write the change in volume as beta times V times delta T, and therefore, the buoyant force, since this is the change in volume, the buoyant force would simply be rho g delta V, which is rho g beta delta T, and the buoyant force per unit volume, which everything in equation of motion is expressed in per unit volume. So, the buoyant force per unit volume would simply be equal to rho g beta delta T. So, this is the form of the buoyant force per unit volume which is used in here, because unlike gravity, the motion here is sustained by a change in temperature. So, everything is expressed in terms of the thermal expansion coefficient, which is an experimental parameter which is measured experimentally for most of the gases over a wide range of temperature. So, it is customary to express the buoyant force in terms of the thermal expansion coefficient. So, utilizing the definition of thermal expansion coefficient, I would be able to obtain what is the change in volume as a result of change in temperature, what is the force, the buoyant force due to that change in the volume, and therefore, we can find out what is the buoyant force per unit volume, which can then be used in equation of motion as the prevalent body force. So, fundamentally I am not doing anything new, I am simply substituting the expression of the buoyant force in the body as the body force term in the equation of motion. So, now with this equation of motion in place, I think we are now in a position to write the equation of energy as well. So, the equation of energy in this case would simply be rho Cp Vy del y of T minus T1, where T is the temperature at any point in the rising film of the fluid, and T1 is a constant temperature, reference temperature. We take this reference temperature to be the temperature far from the wall. So, this is the constant fluid temperature that you would get when you move away from the plate. So, this is simply a constant. However, the temperature in here is going to be a function both of Z and of Y. So, that is why I have to use the partial sign. In the second term would simply be Vz del Z, again T minus T1. In the, so this is the convective flow term, and the second term, that the right hand side what I have is K times del square T minus T1 divided by del Y square plus del square T minus T1 by del Z square. So, in all these cases the left hand side refers to convective heat transfer, the right hand side refers to conductive heat transfer, and there is no heat generation term as well as no viscous dissipation, since the flow is very small, very low velocity flow. So, what I have is then the three equations that I need to solve: equation of continuity, equation of motion, and the equation of motion I express it in terms of the free convection form of the equation of motion, and finally what I have is the equation of energy. Now, if you look closely into these three equations, the temperature rise appears in equation of energy, it also appears in equation of motion. Velocity, the components of velocity present in equation of motion and also in equation of energy. However, it is the presence of the temperature term in both the equation couples these two equations in a more comprehensive way, in a way that we haven't seen before. So, the presence of the temperature term makes it a two-way coupling. The energy equation and the equation of motion are coupled both ways. You won't be able to solve any of the equations without solving the other one, or in other words, both the energy equation and the equation of motion will have to be solved simultaneously. So, that makes it more complicated. So, before we do that, before we attempt to do that, let us first find out what are the boundary conditions for such a case. So, the boundary conditions that we would get for a vertical plate where this is the z direction and this is the y direction, the boundary conditions, the first one is that at y equals 0, due to no slip condition, both Vy and Vz will be 0, and temperature is going to be equal to T naught, where T naught is the temperature of the solid plate and T1 is the temperature of the plate at a point far from it, and therefore, it is a constant temperature. So, both these temperatures are constant temperatures, and y equals infinity, that means at a point far from it, again Vy and Vz both will be 0 and T would be simply equal to T1. So, at a point over here, there is no effect of the solid plate, and therefore, no motion is induced because of the presence of the solid plate, and therefore, all of them are going to be equal to 0. And the third condition is at y equals minus infinity, y equals Vz equals 0. So, y equal to minus infinity refers to a point over here. So, any motion of this is going to be like this. So, therefore, this region remains unaffected by the presence of the solid plate. So, y equals minus infinity is at a point far from the plate and below it, and therefore, at y equals minus infinity, Vy is equal to Vz equal to 0 and T is again going to be equal to T1, which is the temperature of the air surrounding it. The next, so the equation, the two equations will have to be solved with these three boundary conditions. As we have seen so many times, it would be much better if we can non-dimensionalize the entire thing, and in order to do that I define theta, the temperature, as T minus T1, dimensionless temperature, T0 minus T1. The zeta is defined as Z by H. So, this is the dimensionless Z component, and what I have eta, which is the dimensionless Y, which is defined, all these are defined as B by mu alpha H to the power 1/4 times Y. The phi Z, this is the velocity in the Z direction, is mu B alpha H times to the power half times Vz. So, this is the dimensionless Z velocity, and phi Y is the dimensionless Y velocity, which is defined as mu H by alpha cube B to the power 1/4 into Vy, and alpha is k by rho Cp, this is the thermal diffusivity as we have seen before, and B is simply the buoyant force which is present in the system. And these are the different ways by which, these are the different non-dimensionalization parameters which are introduced in it. Again, you can see the derivation and detailed treatment of this equation in your textbook of Bird, Stewart and Lightfoot. I would only discuss about the salient features of the solution and the physical concepts involved. So, it is not important for you to memorize any of these. They are going to be there in their text, and if ever a problem comes in which you have to non-dimensionalize, what could be the non-dimensional parameters, they would be specified in the problem. So, you do not have to invent how to non-dimensionalize a specific variable in order to make the equation more compact. So, do not try ever to memorize this, just try to see the pattern, and be rest assured that it will be provided to you in any exam, and this is given in detail in Bird, Stewart and Lightfoot. So, when you put these non-dimensionalization parameters into the governing equations, what you get is the non-dimensional equations. Non-dimensional equations becomes del phi y by del eta plus del phi z by del zeta. This is the equation of continuity, and the equation of motion becomes phi y del eta of phi z plus phi z del zeta of phi z is equal to del square phi z by del eta square plus theta, where this theta is the temperature term. These are all values of velocity, whereas this theta is nothing but the temperature term. And the equation of energy becomes phi y del theta by del eta plus phi z del theta by del zeta equals del square theta by del eta square. So, this is the convective momentum transport, convective momentum transport, diffusion momentum transport or conductive momentum transport. This is the buoyant body force present in the system. This one is the convective transport of energy. Phi y and phi z refers to the velocities in the y and z direction. This theta is the temperature change with respect to eta and temperature change with respect to zeta, and what you would get here then is this is the conductive term. So, it's when you convert these to convert the boundary conditions, it becomes that at eta equals 0 and eta equals 0 would simply tells you that at y equals 0, that means on the plate there would be no slip condition and the temperature would simply be equal to T0. So, at eta equals 0, both the velocities phi y and phi z would be equal to 0, and the temperature, dimensionless temperature, would be equal to 1 at eta equals infinity, that at a point far from it there would be no velocity and the temperature is going to be equal to T1, and if the temperature is going to be equal to T1, then theta is going to be equal to 0. So, with this geometric condition, I again write phi y equals phi z equals 0 and theta equals 0, and at zeta equals minus infinity, that means at a point where z equals minus infinity, at this point there would be no velocity and the temperature would again be equal to T1. So, theta would be equal to 0. So, is phi y equals phi z equals 0 and your theta would again be 0. So, these three equations will have to be solved with these following boundary conditions. However, an analytic solution to this is still not possible, but we can make an heuristic type of solution and then try to see, is it possible to reduce the problem in such a way that that we can make a solution out of such a complicated system. First of all, if you remember, the left hand side of equation of motion refers to convective transport of momentum. So, if you see the dimensionless form of this equation of motion in here, what you would see is this left hand side where you have the Prandtl number, this refers to convective transport of momentum. But the convective transport of momentum is strongly dependent on the velocities, velocity in the y direction and velocity in the z direction. Rather, convective transport is dependent on velocity. So, if the velocities are very small, then the effect of the left hand side of the Navier-Stokes equation, that is the effect of convective transport, would be small. In the limiting case, when you have creeping flow, you remember we have studied creeping flow before. So, if we have creeping flow, then this entire left hand side can be made equal to 0. But if it is not, here the problem may not be equal to creeping flow, but it is still a slow flow. So, the effect of the left hand side of the Navier-Stokes equation on the final form of the solution should be significantly smaller. So, that is the assumption that we are making. Since free convection flow is characterized by slow upward movement of the fluid, so therefore, we do not expect the effect of convection to be significant on the final solution of the problem. So, we are not saying it is 0 such in the case of creeping flow, but we are saying its effect is going to be small. So, now let us see how we can get the average heat flux, which is Q average, which can simply be equals K by H minus del T del Y at y equals 0. So, this is average heat flux from the wall to the outside is, if you forget about this K, then this would essentially, this part is the average value of del T del Y. So, this average value of del T del Y, which by definition is this multiplied by K with a minus sign, would give you the conductive heat lost by convection, the heat lost by conduction combination methodology from the solid plate to the atmosphere. So, this is nothing but the average of del T del Y. So, if you non-dimensionalize this, you would simply see that it is going to be T0 minus T1 B by mu alpha h to the power 1/4, and instead of temperature gradient, I am going to write dimensionless temperature gradient, which is going to be minus del theta by del eta at eta equals 0 times d zeta. So, these are constants as we have defined before, and we are going to call this the entire thing by a constant, by a number, say we denote C for this entire term, because the rest of the things you can calculate based on the geometry and property. So, it is going to be C K by H times T0 minus T1 Grashof number, Prandtl number to the power 1/4. So, what is Grashof number? Grashof number is defined as, which appears automatically, is rho square beta g h cube delta t by mu square, and Prandtl number we know that it is Cp mu by k. So, what we have then is, if we could evaluate this, then we have an expression for the average heat lost from the solid surface. Now, what is this? We understand that this theta is going to be a function of eta, zeta and Prandtl number. If you look at the governing equation, then this theta would simply be a function of eta, zeta and the constant Prandtl number. So, if theta is a function of eta, zeta, Prandtl number, del theta by del eta at eta equals 0 will only be a function of zeta and Prandtl number. So, if theta is a function of eta, zeta and Prandtl number, then del theta, del eta evaluated at a specific value of eta will no longer be a function of eta, it is only going to be a function of Prandtl number. What we are doing is, we are integrating, it is a definite integral from 0 to 1 over d zeta. Since we are taking a definite integral of the gradient over zeta, it is a definite integral. So, this entire thing cannot be a function of zeta, it can only be a function of Prandtl number. So, what this simple heuristic logic tells us is that this term, which we, in order to evaluate this, we have to solve the partial differential equations, but we do not need to solve it if we look carefully and think about the functional form of theta to be a function of eta, zeta and Prandtl number. Since I am taking the derivative of that at a specific value of eta, it does not remain a function of eta, it is a function of zeta and Prandtl number. So, since I am taking a definite integral over zeta, so it is no longer remain a function of zeta, it is only a function of Prandtl number. So, the entire problem boils down to finding out this as a function of Prandtl number, and we also know that even though it is a function of Prandtl number, it must be a slow or a weak function of Prandtl number, because we have earlier said, since the flow rate is slow in convective heat transfer, at the limiting case it approaches the creeping flow, but this is not a case of creeping flow. We have still very slow flow. Since it is very slow flow, the dependence of the solution on the values of the Prandtl number will be small, will be very small. So, we do not need to solve the equations, we just need to find out what is the value of C, and when experimentally the values of C were calculated for different values of Prandtl number, for Prandtl number equals 0.7, this value is 0.517, for 10 it is 0.61, for 10 square it is 0.65, and for 10 cube it is again 0.65. So, you can see that the value of this C experimentally obtained does not depend strongly on the value of Prandtl number. So, the average heat flux that from a vertical plate would simply be equals 0.6 times K by H T0 minus T1 Grashof number Prandtl number to the power 1/4. So, this is an expression which you have obtained by looking at the governing equation, looking at the significance of each of these terms and recognizing that you do not need to solve the problem. You identified the correct feature of the equation, saying that it is a slow flow. So, the effect of convective heat or mass transfer, convective heat or momentum transfer would be small. So, the integral which you need to calculate from the solution of the coupled PDEs, you do not need to do that. The integral is going to be a function only of Prandtl number, and it is going to be a very weak function of Prandtl number. So if anyone can tell you what is that value of the function for one value of Prandtl number, you are safe to use it over a wide range of Prandtl number, wide range of fluids experiencing different conditions, and you will still be within the limits, still be able to predict what would be the total heat loss from a vertical plate which is placed in a stagnant body of cold fluid. So your analysis makes the solution, makes the requirement of the solution of the PDEs redundant. So here is an example where an analysis and understanding of transport phenomena can reduce your workload greatly in a significant manner. And this is one of the beauties of transport phenomena, study of transport phenomena, which from first principle tells you how to deal with a system from the first principles and arrive at a solution without actually solving the governing equations. So what we see over here is what we have obtained over here is a formula for the average heat lost by the solid surface as a function of K, Grashof number and Prandtl number, which are all thermophysical combinations of thermophysical property. H is the geometry and T0 minus T1 is the imposed temperature gradient. And since by definition your Grashof number contains delta T in this form, so this delta T and this delta T essentially tells you that the Q in natural convection is proportional to delta 2 T to the power 5 by 4. So this is also a relation which directly follows from this expression and which has been widely used, widely cited for the analysis of natural convection.